For Chollet, he views a difference between skill at some task and intelligence. Intelligence for Chollet is the efficiency that you can take whatever information you're starting off with. So this can include like prior knowledge or just your data, and turning that information into new skills that can perform well in some scope of tasks. In fact, I remember it was OpenAI 5, like there was this AI system that could beat the world champions, because like since I've been playing for years, I sort of like know the skill required to play at the highest level. So that was really sort of mind-blowing. But interestingly enough, several years later, like I look back and I don't find the Dota 2 system actually that impressive, just because like, you know, it was trained on like 45,000 years worth of data or something. So it's very inefficient in sort of like the data it's using to acquire those skills, which interestingly sort of links to exactly what I'm working on now, which is how can we, you know, get close to this sort of like human intelligence of efficiently being able to use data to acquire new skills. My name's Alessandro Palmarini. I finished my undergraduate degree last year at the University of Edinburgh in sort of like a artificial intelligence computer science degree. I knew towards like third year, fourth year, and especially doing my undergraduate project, which I guess we'll talk about later, that I loved research. I love working on these sort of problems, but I didn't know exactly what I wanted to work on. I was sort of split between two different directions. So I didn't end up applying for anything following my undergraduate. I just finished my undergraduate, had nothing to do, and just began exploring, reading a lot, trying to basically figure out which problems I wanted to work on most. That is when I stumbled across François Chollet's On the Measure of Intelligence, probably first through the podcast you did with him. And reading that paper was basically very inspiring. I began working on that problem for about a month. And it was during that time that I saw a lot of overlap between some of my ideas that I was having and work that Melanie Mitchell at the Santa Fe Institute, who you also had on the podcast, was doing several decades ago. And so I ended up reaching out to Melanie, asking if there's like, basically saying that I have nothing planned. Is there any chance that I can come over and work with you as like an intern or something? And amazingly enough, that all worked out, and she was able to fund me at the institute where I am now. So working as what's called a post-bac. So I've not done a PhD, in between undergraduate and PhD, doing research.
I'm incredibly jealous. So you get to work with, you know, Melanie Mitchell. I think I look up to her more than anyone else in the entire space. So you're so incredibly lucky.
I am extremely lucky. Yes, Melanie is amazing.
Yeah. She is absolutely. I mean, she did a book on complexity, and then one on you know, like a history of AI.
Right.
I think it's AI for Thinking Machines is the name of it. Melanie is absolutely brilliant. So you're working at the Santa Fe Institute.
Yes.
Tell us about that.
Sure. So the Santa Fe Institute is like a small research institute in Santa Fe. There's not many people working on like computer science and the stuff that Melanie does. Like they're actually very broad. I'd say like the high theme is like complexity science and complex systems, but you have people working in all different areas like theoretical physics, biology, origins of life. There's some historians, sociologists, sort of like a small core, like 12 or 15 resident faculty members, similar number of postdocs, post-bac, and then lots of external faculty members that are constantly sort of coming in and like visiting the institute. So you always have like a very wide range of people there, which is great to interact with. A lot of mathematicians as well.
Yeah. So how's the culture there different from another, you know, any other type of research institution?
One sort of unique thing is they don't have departments, and like the resident faculty, I think they're not even allowed to have groups in like their own labs. Sort of like the allegiance is to the whole institute, and maybe to like stop this specialization, because I think there's a lot of you know, like solving some of the problems that they're interested in at the institute requires this sort of like cross-disciplinary culture. Yeah. So before my undergraduate, actually, I was not. I didn't know I had this interest in AI and computer science, because I was actually a professional gamer. In fact, I remember it was OpenAI 5. Do you know that? Like the
Dota one.
The Dota 2 bot. So I played a MOBA just like Dota. And so I remember being just like mind blown to see that like there was this AI system that could beat the world champions, because like since I've been playing for years, I sort of like know the skill required to play at the highest level. So that was really sort of mind blowing. But like interestingly enough, several years later, like I look back and I don't find like the Dota 2 system actually that impressive, just because like, it was trained on like 45,000 years worth of data or something. So it's very inefficient in sort of like the data it's using to acquire those skills, which interestingly sort of links to exactly what I'm working on now, which is how can we, get closer to this sort of like human intelligence of efficiently being able to use data to acquire new skills.
Yes.
Yeah.
There's a really interesting thing here because, certainly my friend Dan, what he does as a commentator is analysis. And what I'm sure what the best gamers do is this kind of analysis, which is to say they construct skill programs. So given a game, it's quite situational, but some of the skill programs generalize, and you're kind of creating these powerful heuristics that you can use to kind of gain alpha, if you like, to gain an advantage over everyone else. And I can imagine how that experience kind of seeded a fascination with the process of creating these skill programs.
I think absolutely, yes. Yeah. Like I was always fascinated in sort of like in the mind and like how we can actually learn these things to like do better than others. So I would say, it has definitely probably influenced my interest, like my change interest into AI.
Yeah. So what's the difference between what you did as a human and something like, the Dota algorithm?
So the main difference in this, this is mainly like Chollet's ideas, which like I agree with his view of intelligence as being like skill acquisition efficiency rather than skill. So like people have a tendency to confuse like skill output at some task versus intelligence, which is that process of acquiring the skills at that task. So like the Dota 2 bot is insanely skilled. Like it has a lot of skill at some frozen subset of the game, because then as soon as you introduce new changes, that requires basically creating new skills, and that's where it completely breaks down because it's missing that intelligence part of being able to like see a few changes as humans would, like a new hero gets introduced and being able to flexibly adapt to that and create the new skills to like use that hero. Whereas the Dota 2 bot can't do that because it was trained with massive amounts of data on a particular subset of the game, acquired that skill, and like that's sort of it frozen there. So a big difference between skill and intelligence.
Can you give the audience a refresher on Chollet's measure of intelligence?
So for Chollet, he views a difference between skill at some task and intelligence. Intelligence for Chollet is the efficiency that you can take your whatever information you're starting off with. So this can include like prior knowledge or the experience. So like for like training time, for example, like practicing at a game or just your data, and turning that information into new skills that can perform well in some scope of tasks. So you can always arbitrarily like buy more performance, buy more skill at some task by just adding more prior knowledge or more experience. So like the world's best chess engines, they don't really leverage lots of experience, but they have loads of baked in prior knowledge. And so like they struggle to generalize if you were to like change the rules or create new tasks. On the other end, you have like the systems like OpenAI 5 that don't have too much prior knowledge, but they're requiring huge amounts of experience in order to learn that skill. And like he gives a good example, like if you think of locality sensitive hash function in a hash table, like this is already fully equipped to reach maximum skill and maximum performance at any task where you can sort of sample unlimited data as in any video game. So like you just get a new experience, you map that experience to what you should do at that, like in that situation, and then by just sampling more and more experience, you can basically increase your skill, but you're not increasing your intelligence because for Chollet, intelligence is how efficiently you can acquire that skill.
Yes, and I guess he also makes the tangential argument that LLMs are glorified n-gram models. They're like a database,
right? Like
and like the problem is it's so difficult to distinguish memorizing an instance of a thing versus doing the reasoning.
Right. And I'm sure, and I'm pretty sure I've heard Chollet say this, like humans are definitely doing memorization as well, but like we have, I don't think they're completely separated. Like a lot of, and just my own experience as a gamer, Like there are stuff that I would just do so like I would practice basically over and over and over and over again. So it just basically becomes like I see that situation and I can just execute. But it's also full of these situations that I've never seen before, and you sort of have to adapt on the fly based on your existing sort of like building blocks that you're sort of assembling into new skill programs.
Yeah, because there are so many psychological biases that seem to prove that out, like social proof and authority. We use all of these heuristics where we want to be economical. We don't want to do the reasoning. Right. We just kind of do what other people are doing, right. or we just use some heuristics. But we do still have the ability to be creative when we need to.
Absolutely, yeah.
So Chollet created... He didn't just do the measure of intelligence. He actually wanted to have an actionable benchmark for it, which is the ARC challenge. Right. Can you tell the audience about that?
Sure. So ARC is Chollet's sort of answer to how we can go about measuring this aspect of intelligence rather than skill, as many of the sort of AI benchmarks are set up to just measure end performance. For Chollet, there's essentially no task where performing well at that task demonstrates you have intelligence, unless it is some sort of meta task that is evaluating how efficiently you can acquire skills across like a broad range of tasks within some scope, while also controlling for priors and experience. So in ARC, a single task, so it's made up of 1,000 tasks, and a single task in ARC contains a few input-output grid pairs. So you may have 2 or 3 examples. These are like pixelated colored grids demonstrating some underlying transformation. So each pair in the task is non-identical. They look very different at the surface level, but there's some common structure underlying that. And the task for the solver is to essentially induce what this underlying rule is, which is essentially like the shared concept, and use that concept to transform a test input grid that has no output grid and generate the correct output grid. So that is a single ARC task, and Chollet assumes that the only knowledge needed to solve these ARC tasks are what Elizabeth Spelke will call core knowledge. And these are basic things that are assumed to be either innate or learnt very early on by humans. So things like objectness, like the world can be parsed into different objects and they have certain physical properties, like basic numerosity, like counting and comparing like less than or greater than, basic like topology and geometry, simple things like these. And then the experience is controlled because you only get 2 or 3 examples to sort of discover what this underlying rule is.
Very interesting. Yeah, so Chollet comes at this from a kind of nativist in psychology and rationalist perspective, which is that, reasoning is the ability to, create new truths or new knowledge about the world. But it doesn't come from nothing, like empiricists say that it's all derivable from experience. Right. This school of thought is we kind of construct it compositionally from existing knowledge, and we do this, all of these series of deduction, if you like, to build, new models compositionally.
Right.
Now, you cited David Deutsch in your paper.
Yes.
Tell us about that.
Yeah, so David Deutsch might actually be a big reason that I am into research right now, because when I started my degree, I definitely didn't have much of an interest in research. I was just more very interested in like AI systems and coding and programming and all things like that. But reading his book, The Beginning of Infinity, which I can highly recommend for everyone, got me much more interested in sort of bigger, more fundamental questions, and especially like theoretical computer science. In his view of epistemology, which draws from Karl Popper's epistemology, has definitely had a big influence on how I approach all these problems. So, for example, just looking at a single ARC task that has 2 or 3 examples, there's no way you can look at these examples and sort of mechanistically derive the correct program. So, like you said earlier, reasoning about sort of like deducing and building upon these building blocks, I don't think it would, there definitely will be parts of deduction, but a lot of it is induction. It's sort of like guessing. Like there's no way a priori to know how to go from the examples to the program solution. Instead, some form of conjecture or hypothesizing is needed, just as in our scientific theories. Like a very useful slogan from Karl Popper is that like scientific theories are not derived from observations, they're tested on observations. So we will sort of conjecture these theories, and then we will try and interpret the world and see if we can understand the world in terms of those theories. And then there will be mistakes, and those sort of mistakes produce problems, and we try and solve those problems by conjecturing more and then testing on those observations. So I think it's the exact same with these sort of ARC problems or any sort of computer science like program induction type problem. We're translating it into computer science. That form of like guessing is essentially search. So basically, this tells us that some form of search is needed, and the question is, how do we go about doing that efficiently? Because we can somehow do that very efficiently.
Yeah, you raised a very, very important point. So there's this deductive closure. So we can have all of this base knowledge, and we can create these deductive traversals by composing them together. But we would only be able to know for sure whether or not we can produce the test samples.
Right.
We're actually solving a much harder problem. We're trying to generalize, into different instances of the problem. We're only given like 3 instances, and that's when it becomes an inductive problem. And this is actually really, really, really difficult because we have these heuristics in our brain where we just kind of feel that this is probably the correct program, maybe because it's anthropocentric or because it's very simple.
Yes.
And we're actually doing something which more resembles like abduction or induction there.
Right. Yeah, I think so for sure. It can be, one thing that David Deutsch will always say when people think that they are just looking at observations and the theory is sort of, popping into their head based on the observation, that it's actually just a misconception, that really the idea is always there first. And like without the idea first, like we wouldn't even know to interpret some observation in whichever way that we did. So yeah, I think the idea is basically always being generated first, and then we are testing it on the observations. And the same applies to these program induction type problems.
Very interesting. Well, you just said the magic word, program induction. So there's this whole space in computer science called inductive program synthesis. And a lot of people in the ML space wouldn't even have heard of this.
Okay.
So tell us about that.
Sure. So ARC could be viewed as an example task, program induction task. But at a high level, program induction is you're given some specification of a desirable program. And this could come in many forms. And we want to automatically generate a program that satisfies that criteria. So the most common example is like programming by example, where I give you a few input-output pairs relating to a transformation, and we want to automatically generate a program that can transform all the inputs into their respective outputs. So essentially, like we give an example of the functionality or the behavior, and we want to automatically generate a program that matches that behavior. So outside of ARC, I could give you a list of numbers. So I might give you like 3, 2, 1 gets transformed to 1, 2, 3, 6, 8, 1 gets transformed to 1, 6, 8. Give me a program that can sort of generalize beyond this, and then you want to try and discover a sorting algorithm, for example.
Very cool. So where is, obviously I associate this with like MIT and Kevin Ellis and Josh Tannenbaum and so on. So there's a big group of research there. Is that where the locus of the research is? Or?
A lot of the program induction work, especially like the Bayesian program learning, comes from Josh Tannenbaum and like Armando Soler-Lezama's groups at MIT, that's for sure. And the system that I've worked most closely with is called DreamCoder, and that was developed mainly by Kevin Ellis during his PhD at Josh and Armando's lab at MIT. Yes.
Amazing. So DreamCoder might be the coolest algorithm ever created.
It is very cool.
And as you say, that was Kevin and Josh's group. Can you give us the pitch for it?
So DreamCoder, as you said, is a inductive program synthesis system. So as input, you are receiving a large corpus of program induction tasks in some domain. And DreamCoder wants to solve those tasks. So all programs are built out of these primitive operations and elements. And this can be a finite set of elements. or elements and operations, but the way they can be combined to form new programs is infinite. And like as you start looking at programs with more components, then like the number of programs with that many components sort of grows exponentially. So it's sort of, we can think of it as like a search tree, and the search tree is growing exponentially. So if we're not looking at trivial cases, so as we go beyond trivial cases, if we want to discover desirable program solutions, we need a way to simplify search. So DreamCoder is an algorithm that, as it's learning and searching for these program solutions, it's also going to learn how to simplify search for those program solutions. And it will do this in 2 stages. So broadly, there's 2 ways we can reduce or simplify the search problem in this big space of programs. One is by reducing the depth of search, and the other is by reducing the breadth of search. So DreamCoder will reduce the depth of search by creating new library components. And I will explain what that is. So if we start off with, and I should say, when I refer to a library, that's just our initial program operations and elements that we use to, combine together and build new programs. So, for example, if we're coding in Python, it would just be all of Python's basic, Python's grammar, essentially. So if we start, like, imagine if we have a simple library, it just contains like the plus operator and the element 1. Then like we can have the program outputting 1. We can have the program outputting 1 plus 1, 2, or like 1 plus 1 plus 1 outputting 3. So this creates like a program tree. If we were to look at some program in this, like built out of this library, so for example, we could take the program outputting 3, 1 plus 1 plus 1. And if we were to sort of collapse that into its single operation that we add back to our library. So now our library contains plus 1 and the program outputting 3. Now, if we want to build the program outputting 4, we can just do 3 plus 1. So this requires like a depth of 3, as opposed to in our previous library, if we wanted to create the program outputting 4, we'd have to do 1 plus 1 plus 1 plus 1, like a depth of 7. So essentially, by collapsing program components and adding it to our library, we can reduce the depth needed to reach like behaviorally equivalent programs. We can reduce the depth to reach those programs. So that's what's referred to as chunking. We're taking program components, chunking them, and adding it to our library. DreamCoder, as it starts solving problems, and so let's say I give you 100 tasks. Initially, you have no knowledge about the domain, so all you can do is search blindly. Let's say you happen to solve 10 of the tasks by just randomly searching. Once you have those solutions, DreamCoder will look across the solutions for common functionality, sort of the most expressive and common functionality, and it will chunk that into program components and add it to the library. So this is essentially compressing and allowing the algorithms to express its program solutions in fewer components, which of course reduces the depth needed if you were to search for those programs again. It will then reduce the breadth of search by training a neural search policy. So it's basically going to learn a heuristic for how to navigate the search space. It will take its program solutions and it will train a neural network, which is a distribution, to infer, given a task, what are the likely programs to solve that task. And by putting a distribution over library components, you're essentially downweighting certain trajectories in your search space, and this corresponds to reducing the breadth of search. So yeah, it will start searching for, so as an overview, it will start searching for program solutions. As it discovers some program solutions, it's going to look for common functionality. It's going to chunk that functionality and add it to the library, compressing those solutions. It will then train a neural search policy to essentially use that library and infer, given a task, what are likely programs. And once it's trained that neural search policy, it's going to start searching for more solutions. Hopefully this leads it to finding more solutions. And then it can take that like larger set of examples to do the same again. Chunk more functionality, retrain a neural search policy, and iteratively solve more and more programs.
So two quick questions on that. So you said that there's a procedure for looking for common functions, and also there's this program search guiding thing which basically says, I think this program is good at solving this task.
Right.
And that must be done heuristically. So how can you statistically tell whether a program or a function does the thing you think it's going to do?
If we have a single program and we want to basically determine, does this program solve our task, all we need to do is run this program on each of our given inputs and see if we get a desirable output. Of course, so if you want to test this program, then we might assume that there is an underlying program, and so there is a corresponding output grid that we can't see for a test input-only grid. Then we may have a program that transforms all our training input-output pairs, but doesn't transform the input grid into a test input grid into the actual output grid. But if we never receive that output grid, there's no way to tell. Like if we have some magical tester who's like keeping that hidden, then they'll be able to tell us whether or not we have the right program. And if we don't, then we would just have to keep searching for a new one. Does that answer your question?
Yeah, that makes sense. So there's one stage which is where we're actually doing verification. So we're actually running the program and we can see, does it work on the test?
Yes.
But on this neural guided search, isn't there a statistical component, which is that we think that these module, we should search in this direction more than the other direction.
Right.
And that's done with a neural network.
Right.
How does that work, and is it brittle?
So the neural network is essentially parameterizing a distribution, a posterior distribution of over programs given a task. And so this works by like putting a probability distribution over library components, and you can start composing programs that way, as in taking so DreamCoder will actually search by enumerating programs in decreasing likelihood of this distribution, and it's going to keep searching through programs until it hits one that covers the criteria that we just talked about. But yeah, it's a useful point to say that if we have a probability distribution over programs given tasks, then we essentially need a new distribution for every single task. Like every single task has a separate distribution. By using the neural network to map tasks to distributions over tasks, this is what's called like amortized inference. We're using like one function, one set of parameters to specify essentially an infinite number of distributions. Like given any task, it's going to spit out a distribution over programs for that task. And this will be useful for what we'll talk about later.
Yes. I guess it's really interesting because, neural networks are really good at generating ideas. And there's this interesting symbiotic relationship between generating ideas, and of course it has to be sensitive enough to include the correct thing in there, and then we do verification as well.
Right, yes.
So we're sort of like generating ideas and then we're selecting with the verifications.
Right, the verification, is very important here, because we're not just randomly, and this is a big difference between DreamCoder's like wake-sleep algorithm, as they call it, and traditional wake-sleep, which will also use this posterior distribution, but it's just going to sample the distribution once and get so in our case, the latent variables are these programs that we can't see. And in traditional wake-sleep, they'll just sample from the posterior, get a latent sample, and use that to train their model. Whereas in DreamCoder, we're not just sampling, we're actually going to enumerate and verify that we have a correct solution.
Very, very interesting. Yeah. So let's talk about chunking.
Yes.
Because I'm thinking that there are different approaches to doing this. So you could chunk quite greedily, and you might end up with lots of chunks that hardly ever get used. Right. Or you could be quite stingy about it and only chunk if you think it's going to get used a lot. Right. What are the trade-offs there?
Yeah, so this is a very good question, because there's a big trade-off. If we just want to best compress our program solutions, then we should just chunk all of those programs and add them to our library, because now we can express all of those programs in just a single component rather than multiple. But if we think of it in terms of a search view, like we want to simplify search for discovering more program solutions to solve sort of unseen tasks, then every time we chunk a component, we have a new component in our library, and so we are increasing the breadth of our search. So that there's like a strong interplay between successfully reducing the depth of search and successfully reducing the breadth of search. And they're sort of highly reliant on each other. So if we go back to our example of a library containing plus and one, and if we chunk the program outputting free and add it to our library, but our neural search policy doesn't care about using that program outputting free, it still just cares about plus and one, then essentially we've not done anything in terms of reducing the depth of search. Like it is just going to ignore the free operator all the time. So in order to successfully reduce the depth of search, ideally it complements how we are going about reducing the breadth of search.
And just kind of trading off those two things, because there's a kind of aspect ratio. So, there's the breadth and the depth. Do you think a system is more intelligent if it has more depth and it's composing lots of things together? Right. Or do you think, another approach would be just to have a lot of breadth and kind of memorize many different heuristics? Like what are the trade-offs?
Right. That's a very good question. Okay, so this is something that I've not thought much about. So, but it seems like if you have like a lot of breadth, so you have these certain building blocks, like these certain program components, and like some of these may be chunked from existing solutions that we know how to work, then if we have a lot of breadth but we're not going very far, then it means we're sort of making these small variations on the programs. So we're like adding a small number of things which might allow us to generalize to maybe similar cases that are maybe novel, that we've never seen before, but still not requiring much generalization at all. Whereas it's really the depth, like going far away from what you currently know, that will allow for these handling novel situations that require these sort of like very novel and creative ideas. So that's interesting.
Yeah, I mean, it's a similar thing in neural networks. I guess you can think of it both ways, because in some sense, as you go through the layers of a neural network, it's learning more complex features, like high frequency features and so on. But you could also view it in terms of it's reusing kind of like composition. That there's, if you look at the trajectory of the activations in the neural network, it's kind of like it's using compositions of representations, which would make it generalize more.
Right. Yeah, that's a good point.
So you've written this paper called Bayesian Program Learning by Decompiling Amortized Knowledge. So you started with DreamCoder and you've added a very important modification to it.
Yes.
Tell us about that.
We are using the exact same DreamCoder system that I've just described. So it's going to operate in these three sort of stages. You're searching for program solutions, or you're going to chunk program components like these modules and add it to your library. And then you're going to train a neural search policy to use that library input a distribution over how you want to sort of guide search. And then these three stages bootstrap off each other, and you can iteratively learn to solve more problems. What we do differently is, rather than chunk program components based on what best compresses our current solutions, we're going to take a different approach. And intuitively, at a high level, the approach is, given we have this neural network that's guiding search, so essentially it's the one deciding how to go about composing program solutions, why not leverage that knowledge that it's learned for like patterns about how what program solutions are likely to solve a given task, to decide what to chunk. So we're going to look at the functionality that it wants to use most often for creating program solutions. And again, we're hoping that here it's generalized, it's learned some generalizable patterns that might be helpful for unsolved tasks. And can we somehow extract the useful program components that it wants to use and add it to the library so that it can sort of be retrained with the new primitive chunks, allowing it to get to the program solutions it wants faster. So like this ties back into the interplay between chunking to reduce depth in a way that would complement how we are going about using those chunks to reduce breadth of search. And we use the metaphor decompiling because a decompiler will take low-level machine code and try and sort of reverse engineer what the high-level source code might have been that got compiled into that machine code. So here, when we're training a neural search policy, we are essentially compiling in useful information for composing program solutions, and we want to try and extract from those into the weights of the neural network. And we want to extract from those weights useful high-level program components that we can then chunk and add to the library.
Very cool. So I'm going to show a graphic on the screen now, which is the figure from your paper. So you're showing this positive feedback loop. Can you explain this figure?
Sure. So that figure describes the three main stages of DreamCoder. We begin searching for program solutions. As we find more program solutions, we have more examples to infer. So that figure contains two parts. Like the first part is just an overview of pure DreamCoder, the black arrows, and it starts with searching for program solutions. As you discover more program solutions, you can then infer more what would be useful functionality across those program components that you could then chunk and add to your library. Once you do this, you can then retrain a neural search policy to use those program components. And another interesting part of DreamCoder that we haven't described yet is when they're training the neural search policy, they won't just use program solutions that were discovered while they were searching what they call wake, while they were searching for actual program solutions to solve the tasks they were provided. They will also use the current library and prior distribution over that library to generate fantasy examples. So like they'll randomly sample these fantasy programs, they'll run it on certain inputs, and this creates a new task. So now you get these program task pairs that were not observed in sort of the real world, but was sort of created by the system itself. And they'll train the neural search policy on those fantasy samples as well as the real samples. So when we chunk and update our library, we're essentially updating what they call the generative model, and this allows us to then train a better neural search policy. When we train the neural search policy, we're training it to infer the hidden programs given the task, and then we will use this library and search policy to go back to that first stage and search for more program solutions. So this will help us find more program solutions. More program solutions help us make better chunks. The better chunks allow us to generate better fantasy examples, which allows us to train a better neural search policy, and we can just sort of iteratively repeat this procedure. The other part of that diagram is the orange arrow, which says that in the dream decompiling work, we're not just going to take what was given by the wake phase when we were searching for program solutions. We're actually going to use the recognition model that was guiding search to try and help us decide what to chunk in order to reduce the depth of search.
Yes, and to do that, there's a ranking function.
Right.
And that's a really important thing in your paper, because you approached it in a couple of ways. Can you tell us about that?
So we have this high-level idea that we want to somehow extract the useful functionality that the recognition model wants to use. A very simple approach is just look at which functions, which are just programs, subprograms, the recognition model wants to generate with the highest probability averaged across all tasks. So this is like one simple way to do it. A problem with this approach is one, it only provides a ranking. So it can tell us that like function A is preferable over function B, but it doesn't tell us how many functions would be useful to chunk into our library to help the recognition model. The second problem is that like larger functions are naturally harder to generate than smaller functions. So as an example, if we had one function f and we had one subfunction part of f, the larger function will always have lower probability than the smaller function because we have to generate everything in the smaller function plus more components. But if the recognition model was only ever intending to generate the larger function, then it would be more useful to to chunk the larger function than the subfunction, because then we collapse more components and the subfunction has no use elsewhere. So these are sort of two problems with that simple approach, which we try and address in our other approach to decompiling the recognition model.
And tell us about that.
Sure.
This is the one with the Bernoulli distribution.
Yes, this is the one with the Bernoulli distribution.
What is a Bernoulli distribution?
So a Bernoulli distribution is like a coin flip. So we have a binary variable, a binary random variable. It could appear as one state or another state. And so we're going to have sort of a split distribution over these two states that add up to 1. And so our goal is to decide, like, if I give you some function, will this function, if we chunk this function, will the overall benefit for the recognition model, our neural search policy, to generate program solutions across all tasks increase or not? So will net benefit be helpful or not? Because of course we can chunk something, and then if we sort of allocate some probability to this functionality and it's not actually useful for solving our programs, then we're actually going to make things harder to generate our program solutions. So this is our Bernoulli distribution is over this variable that we're constructing of will net benefit be positive or not? And then it's a question of well, how do we calculate this? And there's no way to calculate this exactly without actually going ahead and chunking a component, retraining the neural search policy, and actually checking if it is helpful or not. So essentially, we want to express we want to express this uncertainty with a probabilistic model, sort of systematically saying whether or not chunking some function could be helpful or not. So that's essentially our criteria, and this sort of solves the first problem we had of only giving a ranking, because once you have this distribution, you can start using decision theory, assuming you have some utility function, and basically only chunking if the expected value is positive or not. Although in the paper, we just use the simplest criterion. It's enough to sort of show the strengths of the approach. We don't actually provide a utility function, but in principle, future work could solve this problem. The second problem was we don't want to just chunk based off generation preference, because we had that example of larger functions are harder to generate. We actually want to capture the notion of what would be useful for the recognition model to generate all programs. And so how well we solve that depends on how well the probabilistic model sort of approximates that true distribution.
Yeah, and tell us about the caching scheme.
If we take this distribution of the probability of a function being useful to chunk for the recognition model, we can simplify the problem by introducing tasks and programs and marginalizing them out. And then if we do, just applying basic laws of probability, we can simplify to needing a model of how useful will it be to chunk some function for generating one particular program on one particular task. So this is much easier than what we had before, but we still can't calculate it exactly without chunking and retraining on all tasks. And so we can approximate this distribution with what we call a caching measure, and we use caching to be distinct from chunking. So for us, caching is we have a recognition model, some probability distribution over programs, and we're saying how useful would it be for this distribution to generate a particular program, given it didn't have to generate a subfunction at all. So we're just saying, let's remove the need to sample a particular subfunction, how useful or how much benefit was gained for generating that full program. And we do this with the introduced caching measure, which intuitively is just capturing the relative proportion of sample difficulty removed from generating the full program when you cache that function. So in information theory, you have this notion of surprise, which is the negative log probability of a random variable. So the lower probability some variable is of being generated, the higher the negative log probability, so the higher the surprise. We could also use the word difficulty, if we assume this distribution is generating these variables, then the higher the negative log probability, the higher the difficulty. And so the caching measure is actually very simple. It's just the difficulty or surprise of the function over the difficulty of the full program. So we're just trying to capture the ratio of difficulty of generating the function as part of a program.
You want to maintain some surprise in the system, presumably. Because I'm looking at your posterior marginal over the programs, and maybe we won't use this bit, but obviously you've done all of this Bayesian analysis, and you've computed this this symbolic representation of this marginal, and this must be intractable to compute.
Yes, it is.
What's the relationship between I'm doing this Bayesian analysis and I've got this lovely Bayesian representation of the problem which I'm writing in the paper versus how it's actually implemented?
The actual distribution that I described earlier, how beneficial will it be to chunk some function? When you introduce all the programs and tasks and marginalize over them, it is definitely intractable. So there's several approximations that have to be made to calculate that. One of them is using what's called a particle-based approximation, which is like simply just restricting the set of programs that you're marginalizing over. And DreamCoder also uses this as part of their objective when they're approximating their objective. And then the other one is just using Monte Carlo estimates, where we're using sort of our empirical data as a sample estimate of the real distribution.
Very cool. Very cool.
Yeah.
Tell me about your results.
So when we chunk, according to this dream decompiling scheme, what we see is that we can increase the bootstrapping effect. So we can learn to solve more programs faster than DreamCoder. However, DreamCoder, in like many of the domains, is able to catch up eventually. So like what this basically says is we can, by leveraging the knowledge learned by the neural recognition model, which is being trained on these fantasy samples as well as the real data, we can learn to make more useful chunks when we have very little and constrained experience. And this sort of feeds back into the system, which allows it to solve more tasks. And then we start getting like building a lead. And once we have more tasks, we can learn to make even better chunks and solve more tasks and generalize more. So like performance sort of increases faster and then eventually begins to plateau. And if you look at DreamCoder's performance, it won't increase as fast, but eventually will catch up. And I mean, there's some domains where they both do very similar.
Yeah, Chollet is smiling because Chollet is saying your knowledge acquisition efficiency is better than DreamCoder.
Yes, in some of these domains, yes.
But then the question is, why does it plateau?
Well, eventually it gets too hard to solve the task. So like, and it seems like no more chunks that we begin adding and no more training of the neural recognition model is helping us get to the parts of search space that where these sort of missing program solutions are. So I don't know. I mean, there's also the question of, and I don't think this is the case at all in DreamCoder, but when we chunk and add program components to our library, we are not changing the possible program behaviors that we can construct. So whatever program we create with our new library, we could always take any of our chunked pieces and sort of like explode it into its smaller pieces that were initially used to build it. So that the set of possible programs is the same. What this means is if you start with a library, which in the DreamCoder case, and so ours as well, is fixed, like humans are deciding what that initial library is, then if any program solutions are outside of this program space, then no matter how much chunking you do, you're never going to create a program space that contains those program solutions. So that could also always be a problem in terms of reaching a plateau where you can just never find program solutions. Although I don't think that's the case here.
That makes sense. Well, the question on everyone's minds, and I'm really excited about the ARC challenge.
Yes.
And at the moment, all of the people who are winning are using language models. And,
right.
I mean, obviously, I'm a big fan of Jack Cole and Ryan Greenblatt. Jack's a great guy. I talk to him a lot. But I still feel that Jack's solution is against the spirit of the measure of intelligence.
Right.
Because it's using this big language model, it's doing all this fine-tuning and so on. So I would like to see a solution like yours on the ARC challenge.
Right.
Are you putting an entry in?
I would hope to, if I can. But the problem is that I'm very bad at estimating like how long things will take me. It always takes me way longer than I think so. So I've been working on an approach now since I finished my undergraduate like 1 year ago, and that's what I've been doing mainly at the Santa Fe Institute. And things are starting to look very promising, but a lot of it is mainly in theory. So I have implementations of earlier versions of the project, but then there was like lots of problems, and so I have to go off and try and solve them. And so now I'm not actually at the stage of being able to implement these ideas. There's still a few sort of big problems that I want to solve before I can get to it. But if I was to get to that, I would try and I'm definitely going to try and implement and release a submission when that comes. But whether that will be in time for this deadline, which I think is early November.
Please. Because the thing is, you're going to be famous, man.
But if it works, I don't know, are your questions aimed at our approach to ARC based directly on this? Because my approach is, that's definitely where I started, but like over the year, it's evolved it's not really this at all.
Oh, interesting. So you've got a completely different approach, but it's still similar in principle.
Right. It's very similar in the sense that it's still doing this sort of like combinatorial search, but it's no longer in program space. So Chollet actually gives the example of like deep learning and neural networks, like the learning mechanism there, stochastic gradient descent. It's very computationally efficient. Like you can get a big learning signal and sort of move closer to the correct solution, but it's very data inefficient. Like you require a huge sampling of the operating space in order to make this work. On the other hand, you have program search, which is doing this combinatorial search, which is very data efficient. Like you only need 2 or 3 examples and you can create a generalizable solution by searching through the space and getting and finding something that matches those and automatically generalizes. However, the search at the moment is very computationally inefficient. Like for these non-trivial cases, you have to search through loads of things. So I'm doing a similar sort of combinatorial search that will result in a transformation rule, but it's not searching directly in program space in order to get there. And it sort of has these nice properties that allows the search mechanism to be more efficient, at least than program search and program induction, to essentially like adapt to the feedback you're getting, like prune large parts of the search space and jump to corresponding places more easier.
Amazing. Alessandro, we run out of time, but this has been amazing. Thank you so much for coming on.
Thank you so much for having me. It's been a pleasure talking to you.
Good luck with the ARC entry.
Yeah, if everything goes well, I can maybe come back to share more about it.
Definitely. Thanks so much, man.
Thank you.